urban track club has hired an architect to design an indoor track field house. The owner's priorities are cost and aesthetics, both exterior and interior aesthetics. The site has ample access for equipment on all four sides. From a technical standpoint, caissons, and they shouldn't say piers spelled P-E-R-S, it should be P-I-E-R-S, or rammed aggregate piers are each feasible. Select the best option for the building's foundation. And your choices are caissons, piers, or rammed aggregate piers. All right, let's see what we got. The answer is rammed aggregate piers, and it really becomes a cost issue. Let's take a look. So this is a building that is under construction now. This is a year and a half ago. And so right there where you see where they're digging, they're actually digging, they're redirecting a stream underground. Actually, that's what you have right here, not where they're digging, sorry. Right along here, you have an underground stream. It was always underground, but they fortified it and improved it. And so they have this tunnel, this box culvert that directs the stream underground. It's 300 feet long, so it's a football field long. It's 20 feet wide and 13 feet tall. You can easily drive a car through it. You could probably drive 2 cars through it if you were careful and the cars weren't too big. This is the site down at ground level, and you just see a lot of gravel. And one thing that's going to come into play is there's a lot of gravel because it's super useful for all kinds of things we'll talk about, and it's also super cheap, especially where I live in the mountains where there's quarries everywhere. All right, and here's some more construction, and here's that box culvert. The one that's a football field long. And so they of course redirect the stream temporarily at first, and then they put the box culvert down, and then they redirect the stream back to where it wants to be, or where they intend it to be. I'm not quite sure which, and that's what it looks like. And here's what it looks like inside of it. And there's kind of one of the mouths of it. And again, you see it right here. And it kind of makes a right turn somewhere also. I'm not sure if that's at the beginning or the end. I think it's at the end. Now, there are 3 things that come into play that make a foundation expensive, because the foundation is expensive. I mean, for this particular building, the foundation may be somewhere between, for a building of this size, the foundation is maybe 5 to 15% of the cost of the building. And it's an $85 million building. So let's round up to $100 million just to make the math easy, and because it'll probably go over budget. So you have a $100 million budget, you have a foundation cost of something on the order of $5 million to $15 million. Well, that difference is huge. That's a huge line. The delta of that is like overwhelming. And the thing about foundations is as long as you have a competent foundation that doesn't settle and can support the building properly, you don't get extra credit for having an extra good foundation. It's not like cabinetry where there's like an infinite, or fixtures like faucets and that kind of thing, where there's like almost an infinite spectrum and yawning kind of array of different faucets you could put on your sink or sinks, where some are really expensive and those are better generally, or prettier at least, all the way down to kind of your low sink. It's not like that with foundations. You don't really get extra credit for having a better foundation once it's good enough, because no one can see it anyway. So there's not generally a reason to have an extra good foundation. But because foundations in general are a huge cost, and because some foundations can cost easily 3 times or more other foundations, what we want to do is we really want to reduce the price of our foundation, the cost of our foundation. Now, that said, the kind of difference between the $10 million difference is often 3 things. Number one, let's say 4 things. Number one is their water. So if you're digging your foundation, especially if it's a basement, that's below the water table, and the water table, it doesn't mean if you dig below the water table, it's not like you're always in a puddle in your hole. It just means everything gets muddy because the soil is pretty saturated with below a certain level. The soil is going to be pretty saturated. And anytime you dig a hole, there's going to be more water kind of gradually seeping in. It's not like it floods it automatically if it hasn't been raining. But if you're always working in the mud, then you have to start pumping water out, and that causes weird things to the aquifer. It may cause adjacent buildings to shift around. It's expensive to run that. You have to put the water somewhere. There's environmental concerns. And your equipment's always, no matter how much you pump out, your equipment's still going to be running in mud. So your equipment, everything gets expensive and difficult to do. And you can't bring trucks in for delivery and so forth. So if you're digging below the water table, that is very expensive. That's the first one that's expensive. The second one that's expensive is if you have adjacent buildings. For all the obvious reasons, one being that you can't get equipment in, which was not in play here. When I said you can't get equipment in, I didn't mean equipment to the field house, like, pole vaulting equipment. I meant construction equipment. It's a suburban track club. You can get construction equipment into all four sides of the site. That's not an issue here. But if you have adjacent buildings, it's difficult to get some of the bigger equipment in, like cranes or drills, or backhoes and that kind of thing. B, there's often disruption to the actual building, the buildings that are existing. In fact, there's a classroom building right adjacent to this one. This building itself is going to be labs for the building construction department, ironically, and some restaurants. So it's going to be like a food court. And they hit some rock, which is the third thing that makes it expensive, hitting rock that you have to blast out or dig out. And so they were using, this is called a ram hoe, a hoe ram. That you've seen these things before, that kind of thing, where they're just, bit by bit, just taking that giant oversized, nail and hammering it into the rock and breaking it apart and then, hauling it off. And that is wildly expensive to do. So you prefer not to have to break through rock. And if you have to break through rock, you don't want to break through too much of it. In this case, they were breaking through a little bit of rock, but not only that, the rock was adjacent to the existing classroom building, and the sound, which is always loud, was coupled. In other words, the rock underground was also the same rock that was pressing against the classroom building, and so it was going through the structure of the classroom building, and it was like louder in the classroom building than even outside. Because it was being amplified as almost like the same way that your phone, when it's on a counter and it's on vibrate, is louder than when your phone is, on a pillow vibrating. Anyhow, so that's another reason it can be very expensive. And the final reason is if you have to make a deep foundation. Anytime you're going deep, for all the obvious reasons and cost and equipment, it gets expensive. And generally, for big buildings, you often have to go deep because there's usually this soil. Often the soil is not competent enough. It may be competent enough to hold a house, but in terms of the loads on the soil, when you get something really big like this, the soil is often not able to hold it. So you have a few choices, which we'll get to. Now, the choice they did here is called rammed aggregate piers. And it's really not like the other choices in some way. In some ways, it is kind of a hybrid because it's a little bit of there's another option, which I didn't give you, which is amending the soil. So sometimes we'll actually amend the soil. We'll put maybe some Portland cement in the soil, or we'll replace one type of soil with other types of soil. And that's kind of what's happening here. Is what we're going to do is in 250 different locations around this building, around this site, we're going to drill down like this, and then we're going to fill it with gravel, which is super cheap. And then but we're not going to have to drill down that deep. And we're going to ram the gravel down, and it's going to kind of mushroom out at the bottom. And there's going to be if you can see my mouse, it's going to be, each one is going to have kind of a cone around it where the soil can't be disturbed. This is not this site, but this way you can, it's one of these, that's one of the other things about this type of foundation. It's hard to get a good picture of it because it actually doesn't usually look this clean at the top, because the gravel from this one kind of blends into the gravel from this one, and it winds up, and maybe blends into some of the gravel they put on top of a geotextile that allows for the equipment to drive in and is a different, for a different purpose altogether. So the site doesn't get too muddy for the equipment that's going to, in the delivery trucks. But this is the idea that you're gonna drill down, you're gonna fill it with gravel. gravel. And then, as you're going to see soon, we're going to rest the building on top of it. So each one of these circles, like here and here and here and here, tell me on the chat if you can't see my cursor. Okay. So each one of these circles, each one of these 250 circles is a pier. Oops, is a pier, and I happen to have access to the specs of this. So since specs are such a big part of so many of these exams, really probably all 6 exams, specs are in play. So let's take a minute and just read this portion of the specs. So this is locating the work. 1.4 verification. The surveyor shall verify that the following elements of the work have been furnished, installed in accordance with the contract documents. Piles and drilled piers. Verify locations, elevations, and dimensions. So that's a big one, right? You got to make sure it's in the right spot. I saw a presentation long before it was built, long before it was completed. The Richard Meyer Church of the Year 2000, the Jubilee Church in Rome. It was off by 3 degrees, which is a lot on a big site like that. So there was, I'm sure, a lot of hand wringing. I'm not quite sure what happened, but it all worked out for Richard. Anyhow, submit certification to the owner with a copy to the architect in the form of original drawing signed by the surveyor. So that's like a deliverable that the submittal that the contractor has to do, stating that the work has been accurately located relative to property line. And in general, chapter 0 and chapter 1 have all those kind of miscellaneous things like that. Like just make sure you surveyed it right, and make sure that your construction trailer has night lighting outside of it and has a railing out, whatever. And so here's like one of the drawings of the footer of what it's going to look like. So there's going to be up here. And then there's going to be a spread footing, which is going to bear on the pier. And then what we're going to see is on top of the spread footing, there's a concrete. This is a rammed aggregate pier. Then there's a concrete foundation, either wall or column, that's then going to have a piece of steel on top of it. And so there's this, and even there's 2, or even if there's 1, there's this kind of zone of influence. So there's this area around it that as the building bears down onto the rammed aggregates that are underground, it's going to bear out kind of in a triangle out here. And so we need to not interrupt that. We can't interrupt it with underground conduit, which we're going to talk about in a little while. And we can't interrupt it with other reasons for excavating, like underground, like another pier. So basically, I'm not sure why on one side it's 1-to-1, on the other side it's 1-to-2. I assume it has to do whether it's interior or exterior of the building. But there's this kind of zone where we have to have undisturbed. And it's not always the case, but these particular aggregates, it's often the case. And these particular aggregates they use some Portland cement as a little bit of a binder, so that things kind of act a little bit more like an underground caisson or something, but just a little bit of binder to kind of keep the whole thing together. And I think this is that underneath here. In fact, I'm almost certain it is. So underneath this line of gravel and this line of gravel and over here are kind of the rammed aggregate piers, but when they dumped the gravel, they weren't as neat as the other photo I showed you. So you can't see where each pier ends and the next one begins, but I'm pretty sure those are them. And then on top of them, you see in this case, it's, I can't really tell, frankly. I think it's a foundation wall that's resting on a spread footing, and that spread footing is resting on the aggregate piers. But in other places, it's just like over here, you see it's just a column that's going to come up. And so gravel, as I mentioned, especially where I live in the mountains, and there's like, they literally just take it from the quarry right next door kind of thing. And they'll just put it down. And you can see there's underneath of it, there's right here, there's a geotextile. And so they'll put that, in this case, this is gravel that they're putting to, because they have to bring trucks continually. I mean, if you ever kind of see a construction site this big, and this one's not the biggest by any means you've seen, but if you see a construction site on $100 million project, you will see a lot of construction sites coming all the time. And so they have ways of kind of, doing all kinds of things. One is they have making it so that these big construction delivery trucks and cranes and that kind of thing don't get stuck in the mud. So they just put gravel down. Now, the I'll share with you there was another construction site we used to visit the year before this one. I take my students to visit these every month, and my students at Virginia Tech, and the one before had where they were always putting more gravel down, like constantly, like every month they were putting more gravel down. It was always a mess. And this one, they didn't really seem to have to. And even though this one was, at least as wet as the other one, because they were both actually, there's an underground culvert, box culvert in both cases. They both were actually the same part of the same underground stream, even though they're about 3/4 of a mile from one another. And now that I think about it, but what they did different, I asked them what they did differently on this one where they didn't need that. And they put the geotextile much wider than the area that they wanted to drive on. And they think that's what actually helped a lot because it was the same construction company in both cases. Anyhow, and what these grates do, go ahead and put in the chat what you think these grates do, these kind of steel bars over a pit. See if you know what those do. Yeah, you got it right, Junior. They clean tires. So if there is mud on the tires, some of the mud can be taken off either naturally or maybe they hose it off. I'm not sure. Right over those, that's kind of almost like a welcome mat, but it's more for leaving. They don't want the mud leaving because it makes the roads messy, and campuses like the roads to be clean. And also because we all like our topsoil to stay where it belongs. And no one wants their truck to be messy. Anyhow, so these are in this case, you see the footer, and then there's a block wall being built on top of it. In this case over here, there are columns that are resting on a footer that are again on top of the aggregate piers. Now, why can't we just put the steel on top of the aggregate piers? Go ahead and think about that for a second. It shouldn't be too hard to figure out. There's two reasons we can't. One is, how would we attach it? It's just a bunch of gravel. And so how would you attach it in a kind of a permanent way? And secondly, we don't put steel underground. So generally, concrete and gravel can be underground, but this is a steel structured building. So it goes, from bottom to top, it goes rammed aggregate, and then on top of that is the concrete columns or stem walls. And on top of that is the steel structure. Again, you see it here, more of these coming out, and start to pay attention to these. These you probably can figure out what those are, but those are plywood right now that are putting the leveling bolts in the right places. You see it here and here, and you see this line here connecting them. So they're making sure everything is at the right height because they're going to be bringing the steel in not too long. That's what these look like. So if you ever wondered how they get the bolts, the threaded rod with the nuts at the right place, this is how they do it. So they put either a J bolt down below, which looks like a J, so they can kind of grip onto the concrete in the concrete column that's coming out of the ground on top of the footer. In this case, they just have a threaded rod with a bolt down here at the bottom and a bolt up here at the top. And again, they have this piece of plywood that's there temporarily just to kind of hold it in place. And then they'll cast it into when they're pouring the concrete for the column, they'll cast it into the concrete element. And usually there'll be something like 2 inches. What they'll do is they'll pick one of the bolts and make it exactly at the right height. You saw them with the surveyor and the level string, making sure that was going to happen correctly and everything was plumb and aligned. And then later when they put the steel on, they'll use those 4 bolts and they'll tighten them. They'll turn it a quarter turn or a half a turn or 2 turns clockwise or counterclockwise to get because they want to get the steel plumb. They want to have it vertical. And of course, concrete is not that perfect that you can have, 3 stories of steel exactly vertical just by casting it in. We need to kind of be able to use these bolts to account for tolerances and fudging a little bit once you're on the site. And again, this is what they look like. And so we came back a month later because we come every month, as I mentioned, and this is what had happened a month later. Actually, all of that you see, all the steel you see, took about a week and a half to put in. It's nowhere near all the steel that winds up going in, but it's about a week and a half's worth of steel. Of course, the architects are always like, wow, that went up so quick. But of course, that's ridiculous. It was, it was fabricated in a shop. It was sized. It was, and it does go together quick. It always does. But for some reason, we're always surprised by how long the foundation takes and how long the finishes take. And we're always surprised, even as architects. I understand why lay people would be, but as architects, we're like, man, what is taking that building so long to get out of the ground? And then we're like, man, that building came up so quick when you see the superstructure, whether it be wood or steel. And then we're like, man, that building's taken forever to finish. But it happens every time, and it seems to get us every time. So there are these girders that are some of which are unpainted because they're going to get fireproofing or unprimed. There are some beams. There's some other girders. There are obviously columns. So these columns themselves right here are the ones that are going to go on top of those leveling plates. And these are the ones that we want to be able to make vertical. And then we're going to put, I said there's like a 2-inch space, so that we're going to typically put non-shrink grout in that space. And that'll kind of cover it'll cover it up, make sure nothing gets in there later, and make sure things don't rust. So it'll cover up the bolts in that space between the concrete foundation columns and the steel columns that go on, and the base plate of the steel columns that go on top of them. So there's going to be all the steel in the end, and actually there winds up being a lot more steel, as I mentioned. This is an elevator pit. It's going to be a hydraulic elevator. So they're pouring the walls, the concrete walls of that. So there's some, even though it's a steel building, as is often the case, there's some concrete elements, concrete wall elements to the steel building, if for nothing else, as shear resistance. This is actually what the building looks like a few months ago. So probably a year and a quarter after those other photos. And you see all the waterproofing on top of it. You see the precast concrete that's attached to those steel elements. And the whole thing is really just attached to the steel. So there's going to be stone outboard of that. But that stone, we remember, everything's being held, even though the stone looks like it's going to the ground and being supported by the ground. In reality, just about everything, or at least a huge portion of the stone after a certain height, is being supported by these columns that are on top of this rammed aggregate piers. And again, you see it here and here. And so this is the, kind of a section detail. And it looks like there's precast concrete coming down. You see the air drainage gap, the airplane for the cavity wall. You see the exterior insulation. And somewhere back here is the column, the steel column that's actually holding all this stuff up. The conduit that's coming in is obviously, as I mentioned, has to not only avoid the zone, the cone of shame around the rammed aggregate piers, but also it just so happens, and I bring it up because this is very much in play for a lot of the exams. The owner is the university, the contractor is the contractor, the general contractor. The owner has his own consultant doing AV. So all the audiovisual cabling and stuff is being done by the owner's own consultant. I guess the thought is that either that the owner wants some kind of consistency in its AV systems, so that it can know what's there, it can keep track of it, it can it can make it upgradable as it needs to, and just because it's a shame. It would be a shame if every classroom had a completely different system, where the technicians would have to watch YouTube videos to figure out how to connect one piece of AV equipment to another. So the owner has their own subcontractor. Now, when that happens, and it's not uncommon, especially in specialty situations like AV on a $1.5 billion a year campus like this, it's not unusual for the owner to have some of their own contractors. It wouldn't be unusual for them not to, but it wouldn't be unusual for them to have some of their own subcontractors that they prefer to deal with. And those subcontractors are paid for by the owner. But they're coordinated by the general contractor. And I asked this GC, I said, does that cause any trouble where you're in charge of them, but they're actually not really working for you? And he looked at me like, you have no idea, brother. And he basically said something along the lines of, you have no idea, brother. It was a year and a half ago, but he looked at me like, man, dude, you have no idea. So because it's just, it's an issue. The AV consultant, if one of the other subcontractors, let's say it's the gravel subcontractor, the GC, the general contractor, can say to the gravel subcontractor, don't come on Tuesday because we have an inspector coming, right? And the gravel subcontractor is going to be like, yes, sir, because the general contractor pays and hired the gravel subcontractor. So if the gravel subcontractor wants to be hired again, she's going to make sure that she does what the GC wants. But conversely, the AV contractor that's going to be running the cables through this stuff, well, he's going to be like, but it doesn't matter. It's too late. I already have my men coming on Tuesday. And the GC's going to like, you can't come on Tuesday. It's like, take it up with the owner, man. The owner told us to come on Tuesday. We already have people. Do you want to pay our overtime? Because, because now it's going to be overtime because we don't have you on the schedule any other time. It's going to be Tuesday or never. And so I don't know that happened in this particular case, but that's the kind of thing that happens. So it's a bit of a delicate dance where where a subcontractor that's hired by the owner, it has to be coordinated by the general contractor. You can't have that person coming at a time when the inspector is going to be testing something in that same spot. But you also there are some protections for the general contractor. Like for instance, if the owner's subcontractor delays things, the general contractor will document that and say, "See, it was delayed, but it was not our fault. So please don't be mad at us or charge us." Kind of penalty, which is another issue. It's not technically a penalty, but there's often a $500 a day penalty. Essentially, it's a penalty, although legally it can't be called a penalty for the contractor for every day that they're late. And so it kind of winds up being this weird thing where the contractor will often blame the owner's subcontractor, whether or not the owner's subcontractor was to blame or not. But often the owner subcontractor is to blame. So this is again those specifications. So this is Division 1 general requirements. So you have how is testing and inspecting going to work? This is great. You have this is so master spec, right? You have testing and inspecting services, and you have inspecting and testing services. I hadn't noticed that before. Temporary facilities and controls, temporary project identification, project requirements, field engineering, cutting and patching. And anyhow, they have a lot of the rules that don't specifically belong in any other spot. So there's divisions for metals, and there's divisions for windows and doors, and there's divisions for concrete. But general requirements are a lot of the things that the submittal procedures, a lot of the kind of rules of the game that are set out, like how long does it how by when does this particular submittal need to be there, like we saw before. So I pulled, we were just talking about the underground communication systems. I pulled some of the specs for that. We can take a minute to look at it just to get a sense. It's simultaneously banal and overwhelming at the same time because it's the kind of lists and legalese that we as architects probably didn't get into the profession for, but we find ourselves doing a lot of once we're in the profession, especially if you're designing big buildings. So this is the underground pathways and structures for communication. So this is the AV. Metal. So section includes metal conduit and fitting. So there's like kind of a summary of what the section includes, precast manholes and so forth. There are definitions for what some of these things are. So like, somewhere else it talks about GRC. And so now you can see what that means: galvanized rigid conduit. And of course, with master spec, they're always in the same place because you want the AV consultant that the university hires not to have to look through all, 2,000 pages of the spec document. You want them to have to, you want that particular group of people who are doing the AV to know that they are going to section 27053, 270-543, because that's where it is. But anyhow, include duct bank materials, including spacers, just has kind of all the rules, precast or factory fabricated, fabric, so forth, include duct entry provisions. Some of you guys deal with specs all the time. This is not very interesting to you. Some of the younger people who are in this group probably don't deal with specs as much. Actually, some of the older managerial types might not either. It's kind of a mid-career type thing. But anyhow, metal conduits and fittings, and here's that GRC that I talked about. And then, there'll be performance-based specs. So listed and labeled as defined in NFPA 70 by, so comply with TIA 569-C. So these are different kind of things that will have the, the general requirements for the metal conduit. So, I'm making this up, but it'll say, underground one shall have a rust-proof coating that meets this, that meets a standard of whatever, grams of nickel per linear foot of pipe or whatever. Or it'll say, it shall have no more friction than whatever, or it'll say um, that steel pipe shall be no less than a quarter-inch thickness in the shell of the pipe in the actual thickness of the pipe itself. But anyhow, those things are going to have to go into the building. This particular building, they went in a bit sloppier than some others I've seen. And actually, a little bit later, we came back to visit, and they were waterproofing around these, which is difficult to do, as you might imagine, because this is a great place for water to leak in as the surfaces penetrate the foundation. Anyhow, there's more of this and more of this and more of this. So if we kind of look at the, going back to the original question where we're kind of asking about foundations and how this works. So we have spread footings, which, maybe can handle in this example. It depends on the soil, but it depends on the width of it depends on a whole bunch of things. So there's no such thing as incompetent soil. There's incompetent soil relative to the weight of the building. And so if you're putting a shed on incompetent soil, the soil might be perfectly competent. But if you're putting a bigger building on that same soil, it may not be sufficiently strong. And so we're going to have in this case, a spread footing. It can, in this example, 3,000 pounds per square foot. It can resist with some rammed aggregate piers coming down. Maybe in this case, it's twice as much. And then we have piles or drilled shafts, and drilled shafts are essentially caissons, right? So we have something that's going to go down deeper and deeper, and that's where it gets expensive. So the reason that we're using, in this case, the rammed aggregate piers is because, as I mentioned, it's not deep. And it's gravel, and gravel is cheap. And so if you look at a caisson, it'll go through the pore bearing soil. And again, it may not be that poor. It just may be too poor for a building of that height, that size. And then often caissons will bell out. How do we get the bell? I'm pretty sure, and you guys can correct me if I'm wrong, but I'm pretty sure I've seen it before where when they do the caisson, they essentially, if you can think of an umbrella, that little tab that in the umbrella shaft that sticks out, that'll, you kind of, when you're opening an umbrella, you know how you kind of push it beyond the little tab and then the tab clicks into place. Well, you drill down and then a little tab opens up, and that's what bells out the bottom, and it gives some more bearing, and it's going to be, typically bear down into either some really, really good soil or some rock. And so we have belled caissons, which is what I just drew. So we have the poor soil, and we have the either good soil or the rock. And we're going to put a belled caisson down. Well, that's expensive because you have to go deep, and you have to put all that concrete in there, and you have to put all that rebar in there. Or we can put a socketed caisson, which is the same thing. In both cases, a caisson, they're going to drill it out, and the soil itself is going to become the formwork for what's going to become the concrete, the reinforced concrete. And so the concrete itself is expensive, and the reinforcing rebar is expensive, both in terms of man hours and time and actual material. Piles are a little different; they're made somewhere else, and so we're not using the soil as the formwork for the pile. A pile could be wood; you see that all the time in telephone poles at the beach. A pile could be steel; it could be precast concrete. But with piles, you're going to bang, 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 doom, 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 with the pile driver. So those of you guys who are wrestling fans, that's where the pile driver idea comes from. And the pile driver is going to, bam, just, kind of hammer these nails in deeper and deeper. And then, of course, the length of one can only be limited to a truck bed, which is, I don't know, 50-some feet long, 54 feet long. And so every so many feet, they're going to kind of attach another one to it, and they're going to leave the precast concrete or the steel or the wood piling in. If it's an end-bearing pile, again, it's going to go all the way down to the competent soil or to the rock. And then there are friction piles. That's the ones we see in the sand in a beach situation where they're driving telephone poles into the sand. And that's just what it sounds like. Instead of an end bearing, they're just the friction around it is going to keep the building up, especially if the building isn't too heavy, like a house. And generally, that's the same principle as if you stuck a straw in the sand. There's enough friction that it can hold some weight. And if you stuck a shovel in the sand or something like that, it could hold some more, and so forth. This is from Fundamentals of Building Construction, I think. But anyhow, it's the belt caisson, the socketed caisson, the end bearing pile, and the friction pile. And so here's what the caissons look like. They have these big kind of things that they drill down in, and they'll start drilling in. These are the bits, and as they were, and they kind of attach one to the other. I don't think they leave the metal in. I'm pretty sure they take it out and reuse it and fill it with concrete. You can tell me on the chat if I'm wrong about that, but I'm pretty sure they take the metal back out. And then, of course, there's all the rebar and all the manpower that it takes to put in, weld the rebar and put in the rebar. Now, piers, one of your choices was piers. Piers is a little bit fuzzy in this case. What's a pier? A pier is, technically caissons are a type of pier, underground pier, foundation pier. So having the choice caisson and having the choice pier should kind of give it away that it's neither of them, because you can't have a pier and a caisson, because a caisson is a pier and a pier is a caisson. There's another type of, especially for houses, there's another type of a pier foundation called pier and beam, which is just what it sounds like. So there are these kind of sonotubes that'll go into the ground, and then we'll put beams on top of them, especially for if we have a crawl space or a deck or something like that. But sometimes these are also just called piers, when you have poured in place concrete elements that go underground. All right. That concludes this. Actually, let me go back and read the question again, because I think it's probably worth doing that. I thought I had the question again in a later place, but I guess I did not have it. It's like the last 40 minutes of your life being revisited. So here we're saying a suburban track club. Okay, I made it suburban just because I made it clear that there's probably no other buildings around it. And I made that more clear when I said there's access for equipment on all four sides. So there's, if there was no room around it, maybe it would be harder to do rammed aggregate piers, because you couldn't, if you have one building right against another, then you don't have that cone of undisturbed soil to spread the weight over. But anyhow, that's not the case here. It's hired an architect to design an indoor track field house, a medium-sized building, medium/big-sized building. The owner's priorities are cost and aesthetics. So cost is often the case in an owner. And that's where the rammed aggregate piers come in, because they're cheaper. That's really the only reason we're choosing them, because it's not like they're better or worse. They just all do a good enough job, and you don't get any extra points for supporting a building that's heavier than the building you're building. Anyhow, and aesthetics, both interior and exterior. So maybe in this case, we save $10 million by using rammed aggregate piers that we could spend on the interior and exterior of the building. You can get a lot of pretty good finishes for $10 million, even on a big building. The site is end blocks is for equipment on all four sides. And from a technical standpoint, caissons, piers, or rammed aggregate piers are each feasible. Now, again, piers, are spelled wrong, but also it's not, piers are kind of a vague thing. Select the best option for the building's foundation. So that's why the best option is rammed aggregate. All right, let's do our 40 seconds of architecture, just to remind us why we're all in this profession. Because this stuff is pretty interesting, but let's make something beautiful. Or let's look at it. This is a Charlottesville, Virginia firm called Bushman Dreyfus. There's an apartment they did somewhere, can't remember where. And this is a house they did, I think in Virginia. All right. If you have a question, you can go ahead and raise your hand. I prefer you to raise your hand and do a Q&A. If I have time, I'll get to the Q&As. But if you have a Q&A, raise your hand. It just works better if someone has a question and other people can hear it. It's better to have it's better for you and I to have a conversation than for people to listen to me read your question and then tell you the answer. So please raise your hand, and then once you're unmuted, you can start talking. While we're waiting for people to raise your hand, I will read some of the questions. Can you repeat the 4 factors affecting foundation cost? Yes, they are in no particular order, going down below the water table. So if it's going to be muddy and a mess, that makes it much more expensive. Blasting out any rock makes it much more expensive. With the caveat, and NCARB doesn't kind of take this into play, but you should know if you're building a 90-story tower, really, really big building, having shallow rock might not be a bad thing because you might not have to go that deep to get to something that can support your building. But generally, shallow rock is not a good thing, especially if you have a basement or you need to get below the frost line. So if you have rock at 1 foot down and the frost line is 3.5 feet down, that's not going to be an inexpensive foundation. You may want to think about putting your building somewhere else on that site. So shallow rock, wet, adjacent buildings, if there are buildings right up against it, both because you may damage them as you're starting to pound piles into the ground, and you may limit the number of options you have for getting equipment in and for putting the roots of your building down if there's a building right next to it. So having adjacent buildings, especially if they're need to be quiet and operable and people need access to them. It's one thing if it's a warehouse with no one there, but if you have all kinds of people going in and out and you have all this mud and construction debris around, that becomes difficult. So that's an issue with the foundation. And if you have to dig deep. So if you have to go down to the caisson world and the bearing piles world and the caisson world, these are very, very generally very expensive. Depending, who knows how that deep you have to go? It wouldn't be unusual to have to go 60 or 70 feet down. So we're talking about, a 6 or 7 story underground building out of concrete, maybe not a whole building, but you get the idea. To support your building that's going to go 4 stories up, that's super, super expensive. And we use rammed aggregate pier instead of piles in low bearing capacity soil. That's an engineering question. So you couldn't use it like if it was, I've never seen rammed aggregate piers in like sandy soil, because when they ram them down, the sand would just bulge out. I'm not quite sure how it works in silt either. I'm not sure how much clay has to happen, but this is kind of a soils and civil engineering question and a very specific, like how heavy is your building, how concentrated are the point loads in your building as they go to the ground, and what type of soil do you have? Under what conditions are rammed aggregate piers not suitable? Again, I think I've never seen them in sand. You can ask ChatGPT to see if they can be used in sand, but I don't think they're good in sand. They're obviously not good in rock because they're not distributing the weight. If you're building on rock, you can just plop it on the rock. You don't have to distribute it. If you have a very light building, you probably wouldn't need it. Like if you had a house, typically. And the question is, I'm not clear why rammed aggregate piers are better than traditional piers for the subject project. It's because they're not deep and they're cheap. They're just some gravel in a shallow hole, as opposed to a whole lot of concrete and rebar in a very deep hole. So it may go a half a story down instead of 7 stories down. So it's just cheaper. It's a money issue through and through. All right, Shruti, go ahead and you can hopefully unmute yourself. If not, I can do that for you.
Yep, I think I can talk.
Yep.
I just have a quick question. Would your answer differ based on a seismic zone difference? And then
that's a good question.
If your site is on underground mines, then how do you kind of deal with that?
That's pretty specific.
Yeah.
So seismic, I'm not sure. Maybe some of you guys who live in seismic areas and have experience in that can share. I don't know, because you would be afraid of liquefaction, where if the soil is super wet and you have a certain type of soil and you have an earthquake, the soil can turn to liquid, and then your rammed aggregate pier is not so rammed anymore. It's not so compact anymore. So I do wonder if that would be in play in a seismic zone. I have no idea if you had a mine underneath. If you had anytime they have an exotic situation like that, basically the answer is you probably want to go down to bedrock. So my guess would be caissons would be more in play. If you thought there might be a cavity underneath you, so you start ramming down, and then all the gravel just pops through to the mine underneath. That's certainly something that would happen in my area of the country where there's all kinds of underground mines. But I know of nothing specific about the mine. But I think in general, when you see something exotic like that, it could be a distractor, but typically it's telling you there's a giant open hole underneath. So we need to have, and if there's a mine underneath, you couldn't really do a caisson unless you you obviously would need to kind of keep some kind of formwork in and pour the concrete in that, or maybe a slurry wall or something like that. You'd have to, the earth itself would not be able to provide that kind of resistance anymore. So I guess with a mine, you might do a pile driving, but you wouldn't want to, if you have caves or mines, you wouldn't want a situation where you're ramming the pile in, bam, 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 just like hammering a nail in, and then all of a sudden the pile just disappears completely because it falls into a giant cave, because those caves can be many, many stories tall, much taller than they can be much, much taller than the pile that's driving into them. So, but my guess would be that that for a mine underneath, or any kind of cavity underneath like that, you would probably want a pile. That's a guess, though.
All right. Thank you.
All right, guys. It was great to see you again, even though I didn't see you. Take care, guys. Good night. Get licensed.